All right, in this video, we want to look at three very special approximations for areas under curves. And this will be the right endpoint approximation, the left endpoint approximation, and the midpoint approximation. So these are basically, remember the xi stars that we chose in the subintervals. We're just saying that we'll let our sample point be on the right, on the left, or take the sample point to be the midpoint of the interval. And we will also take those x sub i's, we'll take that to be a uniform partition. In other words, we want the widths of all of those rectangles to be the same. Before, we didn't specify that they had to be the same. So in this case, we want them all to be the same. And I'll try to give a better explanation of what I just said in a couple seconds here. So anyway, here's the area that we want to approximate, and in this case, we'll approximate a thing that we already know the answer, just so we can get a feel that these approximations are okay, that that these things are good enough. So we want to use these three things to approximate the area under the curve y equals x plus 1 on the interval from 0 to 2. So we already know what the area of this region is, right? This is a trapezoid with our base 2, a base 1, and then the height from here to here. So we know that the area of this region, we know that this thing is going to be 4, right? So our approximation should be close to 4. And so let's see what we mean by each one of these things using this example, x plus 1 on the interval from 0 to 2. Okay, so let's look at the right endpoint approximation for the area under the function x plus 1 on the interval from 0 to 2. And we want to approximate using 6 rectangles in this case. So I haven't drawn a complete picture, but I've drawn the line. And so the function, remember, we saw what it looks like, something like this. And so the area of the first rectangle, we will use the right, so here's the first subinterval. We will use the right endpoint to determine the height. So here's the area of the first rectangle. For the second one, here's the second subinterval. We will use the right endpoint of the second subinterval to determine the height, right? Keep doing this until you reach the end. So the third subinterval, here's the height of the third rectangle, the height of the fourth rectangle, the fifth rectangle, and then the sixth rectangle. I'm sort of out of the screen now, so basically there that is. So I'm going to find the areas of each one of these rectangles and then add them up, and that will be the right endpoint approximation using 6 rectangles. And remember, the answer that we get should be something close to the actual area, which is 4. Okay, so how did I get all these rectangles? So step number 1 is to look at the width of each one of these rectangles. So I want this partition to be uniform. Since I'm using 6 rectangles, I will take my interval from 0 to 2, right? So my interval goes from A to B. In this case, it goes from 0 to 2. And I will divide by 6, right, the number of rectangles. So the width of each one of these things is 1/3. So I start at 0 and add 1/3 and then add 1/3 and keep doing that until I reach the other endpoint, which is 2. Right, so that will give me 6 equally spaced subintervals. Right, so let's use I as my counter. Right, so I equals 1 is the first subinterval. I equals 2 is the second subinterval. 3, 4, 5, and 6, right, because we're using 6 rectangles. Because we are using the right endpoint approximation, the sample point that I will use to determine the height, again, is the right-hand endpoint. So my x1 star is going to be the right endpoint of this subinterval, which is 1/3. My x2 star, the right endpoint of the second interval, 2/3. x3 star, right, the right endpoint of the third interval, so that's 3/3 or 1. And then you keep going just like that so you can see what the general x sub I star is going to be. And now to find the height of each one of these, again, I'm going to take the right endpoint and plug it into the function x plus 1. So when I plug 1/3 into x plus 1, I get 4/3. When I plug 2/3 into x plus 1, I get 5/3, so on and so forth. So you want to do that for all 6 of these right endpoints to give us the height of 6 rectangles. And so now to find the area of each one of these rectangles, I'm just going to take the height. So this column gives me the height. Here is the width. So I just want to multiply the width times the height in each one of these cases. The width is always 1/3 everywhere. That's not going to change. And so here I just get 1/3 times 4/3, 1/3 times 5/3, blah, blah, blah. So each one of these, right, this is the area of the first rectangle, the area of the second rectangle, the area of the third rectangle, so on and so forth. So now, to find the approximation R6, I just need to add all of these things up. So let's do that now, and then we will compare it with the actual area. Okay, so after we filled out that table and we got the area of each of the 6 rectangles, again, we're looking at the right endpoint approximation using 6 rectangles. We add up all those areas, and that will give us an approximation for the area under the line y equals x plus 1. So remember again, the function that we are looking at is x plus 1, and we were looking at that on the interval from 0 to 2. And we computed that the actual area was 4. So let's see how good our approximation is. So remember, the approximation, the right endpoint approximation using 6 rectangles, right? We're going to add up all of the areas. So we're going to add up these 6 areas. Remember, I started at 1 and I stopped at 6, at n equals 6. And so here was the height and here was the width. And remember, the width of each one of these things was 1/3, right? We took 2 minus 0 divided by 6. That gave us 1/3. So we've got the width, and then the height of the first rectangle was 4/3. The height of the second rectangle was 5/3. Blah, blah, blah. The height of the last rectangle was 9/3. So from here, right, so this notation really just means this. And now we can factor out a 1/3 because the width is always the same in all of them. So I can factor out the width, which is 1/3. And so now I just need to add all these things up. And so really what you can do is just add up all the numerators and then divide by 3 and then multiply by 1/3. So in this situation, we get 13/3. And 13/3 is 4 1/3. That's pretty good. That's approximately equal to 4. So off by 1/3 is okay. Now, the more rectangles we use, the better this approximation will get. In other words, the smaller that this fraction, this leftover part, will get. So maybe it would be a good exercise for you to check like R8 and see that this leftover fraction actually gets smaller. In other words, it gets closer to 4. Okay. Here's the approximation to the same area. Now we want to use left endpoints and see what happens in that case. So again, I want to use 6 rectangles. Here we will use the left endpoint approximation, and we are approximating the area under this curve, y equals x plus 1, and we are on the interval from 0 to 2. So again, in order to determine the width, we want to do the same thing as before. We want to get a uniform partition. So basically, we want all of the widths to be the same. So again, I will take b minus a, right? So b minus a over the number of rectangles. So 2 minus 0 over 6. So I get 1/3. Again, I'm going to get 1/3. And in fact, all of these approximations, since I'm using 6 rectangles on the interval from 0 to 2, the width is always going to be a third. Okay, so now again, I is my counter, and I'm going to count 6 rectangles. So now, instead of the right endpoint, now I'm going to choose the left endpoint. So for my first rectangle, I'm going to use the left endpoint of the first subinterval, and that's going to give me the height of my first rectangle. Right, so when I plug in 0 to the function, right, I'm just going to get a 1. So that's how I got this one. And now for the second subinterval, right, I'm going to use the left endpoint of the subinterval to determine the height of my second rectangle. So there's what my second rectangle is going to look like. And so for the second, when I is equal to 2, in other words, my second rectangle, the width is 1/3. The height now is going to be take 1/3, plug it into the function, so I get 4/3. That's where this comes from. And now for the third subinterval, right, I want to use the left endpoint to determine the height of the third rectangle. So my xi star is now 2/3. So x3 star is 2/3. And then I take 2/3 and plug it into the function x plus 1. And when I do that, I get 5/3. So now you want to do this all the way till you reach the end here. So here's my third rectangle, whose height is determined by the left endpoint. My fourth rectangle, that height will be determined by the left endpoint. Here's the fifth one, and then here is the last one, the sixth one. So now, here are the 6 rectangles that I'm going to use to approximate the height. You can see in the last one, when we used the right endpoint, the rectangles were above the curve, and so my approximation was an overestimate. The right endpoint approximation for this example was an overestimate. We should expect now that the left endpoint approximation will be an underestimate. So instead of plus some fraction, right, instead of 4 plus some fraction, we should get 4 minus some fraction. So now, what are the areas of each of these rectangles? Well, just take the height and multiply by the width in each case. So I'm going to take this column and multiply everything in this column by 1/3 to get the area of these 6 rectangles. So now, in order to find the approximation L6, I just need to add up everything in this column, and that'll do it. So for the left endpoint approximation, L6, using 6 rectangles, right? We're going to add up 6 things. So I started at 1 and stopped at 6. And then we've got the height of each rectangle times the width of each rectangle. Again, this width was 1/3. That's going to be constant, so we can factor it out. So here's adding up the 6 areas, right? Areas of the 6 rectangles. Each one of them has a third in it, so I can factor that 1/3 out. And so now I'm left with 1 plus 4/3 plus 5/3, blah, 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 plus 8/3. And so you work this out, you get 11/3. This is the same thing as 4 minus 1/3, right? Again, this is less than 4, as we expected. It should be an underestimate. The right endpoint approximation was an overestimate. But anyway, this is close, right, close-ish to the actual area, which is 4. Now let's look at the midpoint approximation. We'll do that very quickly. All right, last thing we want to do is look at the midpoint approximation using 6 rectangles. So this is M6. So again, it's the same subintervals every time, right? The subintervals are determined by b minus a over 6. So 2 minus 0 over 6 is 1/3. So that's going to be the width of every rectangle no matter what, just like it was in the last 2 examples. So now, in order to find the height, I want to use the midpoint of the first subinterval. So the midpoint between 0 and 1/3, that's going to be 0 plus 1/3 over 2, which is 1 over 6. So using this midpoint, right, I can see that the area of the first rectangle is going to be given by this thing, right? Or the height of the first rectangle is given by plugging in 1/6, right? 1/6 into the function. So this is my x1 star, and then the height of this rectangle, I will take this x1 star and plug it into the function x plus 1, and so I get 7/6. And now the area of the first rectangle, it's 7/6 times 1/3, just like we've done a bunch of times. And as you can see, the height of this, right, the height of this rectangle, it's got, the function is a little bit below the height of this rectangle and a little bit above. So this approximation should be better than both of the previous ones. In fact, when we go through and add these things up, and I'm going to leave that as an exercise for you to do, when you go through and add up all of these areas, you will actually get 4, right? Because the little bit below and the little bit above is actually going to cancel out. So in this case, right, the next rectangle, here's the height. Not drawing that very well. So again, we get a little bit above, a little bit below, and right, using the sample point, the midpoint between 1/3 and 2/3, right, I add these two things up, I get 3/3, and divide by 2, that's going to give me 3/6, right? That's how you find the midpoint of each one of these subintervals, right? So the midpoint, my x, right, so this is x2 star, right, the sample point for the second rectangle. x3 star, I'm going to add the endpoints, 2/3 plus 3/3, that's 5/3, and divide by 2, that's 5/6, right? Take 5/6 and plug it into the function to get the height of the third rectangle. Again, we get a little bit above and a little bit below, and so the same thing is going to happen all the way across. Right, so you can see this midpoint approximation, at least in the linear case, is going to be a much better approximation than the left or the right endpoint. In fact, in this case, M6 is going to be equal to 4. So check that M6 is actually equal to 4. And in fact, if you want to prove a theorem, if you want to approximate the area under any line on some closed interval from A to B, then the midpoint approximation will give you the exact answer. That would be a good exercise. Okay.